Hello, in the previous video, we saw how to write the code from scratch to train a linear model. In this video, we are going to rewrite the same code, but this time we are going to use some PyTorch functions that makes the process of writing the code much easier for us. Okay, let's start. In the last session, we saw how to train a linear model using a stochastic gradient descent. If you remember, first we generated a synthetic data, like this one, that we have x as the input and y as the output, and then we initialize w and b, and then we define our linear models w times x plus b, and we get y hat, and then we calculated our loss function, and then we used function dot backward to calculate w dot grad and b dot grad. We updated our w and b. After we trained the model, we are able to fit a line to our data, and if you look at the loss function, we can see we can minimize the loss function very quickly because we are using a stochastic gradient descent. So far our model is just a linear model. It's very simple, and as we go forward we want to have more complex models. It is nice to have a separate function to calculate this y hat. Let's do that. Here I can define a function. I can call it forward, and input to that is x, and output of that is y hat. And the function is going to be this, is a y hat equals w times x plus b. Now I have the function forward. I can come and actually use that here. So instead of this line, we say y hat equals forward x. Okay, first I need to run forward. Let me also initialize w and b again. We run forward and we can train it for 10 epochs. And we can see that is working correctly. After 10 epochs, we are able to minimize the function. So now inside this forward function, I can have more complex functions for calculating y hat, and it is nicer and more organized. Okay, now let's see here. We have initializations of the weights w and b here, and then I have a function forward here. So it's gonna be nice if I can create a class, and in the constructor of the class I could initialize w and b, and then I can have the forward as a method of that class. Let's do that. Class, let's call it linear model. First we define our constructor. We say define init self. We need initial value for w, and initial value for the bias. Now we say self.w equals, and self.b equals. Okay, now we have w and b defined. Let's define our method. We say define forward self x, and our y hat now is self w times x plus self dot b, and we return y hat. Okay, I can also comment out this forward function. Okay, now we have a class that initializes w and b, and we have the function in it. Okay, let's have an instance for this class. We could say model is the instance of the class, and for the class linear model, and we already have the initial value for w and b, so it's going to be 0.1 and 0.2. And if you just want, you can look at the model w. So let's do that. Let me run the class. So we can see the model w now is 0.1 and requires grad is true, because that is what we defined as the w here. Okay, and we can also look at the model dot bias. Okay, we have W and B defined in our class, and inside our main loop now we can use this model instance. So let's do that. So we could come and say, and here instead of y hat, I can say this capital Y hat is the one that we use for plotting the loss. So let's do that. So we say model dot forward. For getting access to the method of that instance, we need to use the dot forward because that is the function here. Okay, and then I need to do the same thing for here. I say model dot forward. Now that's my y hat, and here again I can say model dot forward x. Okay, for updating W and B, I also need to put the model in front of them. Model, because W and B are now related to the object model. Okay, for updating W and B and zeroing out the gradients, we use these 4 lines. And is there anything else that I need to change? Again, here I need that model for plotting the value of the W and B. And I think we are good. So let's run it again. Let's run the class to initialize the values and run it for 10 epochs. Okay, it seems it's working correctly. And let's look at the loss function, and we can see we got the exact same loss function. Now we have this class that we initialize W and B in the constructor, and we have this forward method inside our class, and it is much more organized. Now let's go for the next step. So we can see, so here we have a simple linear function, and in future we would have much more complex functions. But just for these examples, let's see how can we use PyTorch functions to do the linear modeling. So for doing that, let's do this. We can say from torch.nn import linear. It's gonna import for us a function called linear. And let's say I have linear model 1, for example. And this is gonna be linear. A hint here that is telling us that the first argument that we need to pass is an integer called input features. And that's the dimensionality of our input. For us, it is 1 because x is only 1 dimension. And the second argument is our output feature. That one is also 1 for this example. Okay. And by default, the bias is true, which we want to keep the bias. And if we do that, now we define our linear model. We can also print W and B related to this linear model we just defined. If we use the function .parameters, we should be able to print W and B related to this linear model we just defined. And we can see we get a number here that is our W, and this number is our B. And if we run it again, you get a different number. So by default, the PyTorch function linear is going to initialize W and B with a very small number. So every time you run it, you get a different number. Okay. Here we explicitly told that we want this 0.1 or 0.2 bit our initialized number, but PyTorch by default is going to initialize randomly for us, which is fine. Now let's go forward and define a class that use this PyTorch functions in it. So for doing that, the first thing that I need to do is to import nn. So we say from torch import nn. And then we are going to define the class. We say class. Let's give it the same name. We say linear model. And inside the parentheses, we are going to use the nn.module. Okay. And then we define our constructor. We say define self input size, output size. These input and output size are the input and output size of our linear model. For us, for this specific example, both of them are 1. And then we have the inheritance of nn.module. And we say super, name of our current function, which is linear model, and then self dot init. Okay, now we have everything of init related to nn.module in our class. Now we define our model. We say self dot linear1 equals nn dot linear input size and output size. Okay. You remember input and output when we give them to this linear function. So it's going to define that model for us, and it's going to initialize W and B for us. Here, when we define it for the first time in the constructor, it's going to initialize W and B for us. Now we have our constructor. Let's define our forward. We say define forward input X and Y hat equals self dot linear1 X and return Y hat. Okay, this time I don't need to access W and B because those are both inside the linear one, and the linear one knows that that is the function it's gonna do is W times X plus B. Okay, now we have this class. Let's define our object. So we say model equals linear model, and we need to give 2 inputs. The first one is the input size is 1, and the second one is output size, that is also 1, because the dimension of X is 1 and dimension of target Y is 1. Okay, now we define our model. Let's use that inside our for loop. For doing that, we say Y hat equals model X. I don't need to use dot forward anymore, because when we use this nn.module, whenever we call a function, automatically it's gonna go and run the forward. So we don't need to use dot forward anymore, because whenever I run the model X, it's gonna go and automatically do dot forward for that. Okay, again here I say Y hat equals model X, and here as well for plotting equals model X. Again, the main reason that we are not using this dot forward anymore is that inside this nn.module, whenever we call a function, it's gonna go and run the dot forward automatically. So we don't need to use dot forward explicitly like the previous example. So we just use model X. Okay, and we also now need to do a little modifications here. So let me do that. This time, instead of model.w.data, we use model.linear1.weight.data, and instead of model.b.data, we use this one. So if we do that, we should be able to update it. Also, we need to change this line to make sure that we are able to plot the W and B. Okay, let's initialize again and train the model again. Okay, we are able to train the model again, and we can see the loss function. Okay, we defined this class here that initially we defined what function we want to use from PyTorch, and then inside the forward method we define how we are going to use those functions. For example, here we define linear1 and then we use that inside our forward function. So this is gonna be actually a very general structure of using PyTorch functions and defining models in PyTorch. For example, instead of only having one linear model in these examples, we could have multiple linear models or nonlinear models and many different types of predefined functions in PyTorch. But we saw also for this simple example here, which we only have one linear model and it only has one W and one B. So updating W and B is actually very tedious if we want to write it down. But PyTorch has a capability that makes this process much easier for us. For doing that, from Torch, we import optim stands for optimization, and then we say optimizer equals optim dot. We are going to use the stochastic gradient descent. We say stochastic gradient descent, and then we are going to put the parameters that we want to be optimized. So we say model dot parameters, and then I'm going to define the learning rate. Okay, so if you remember, our learning rate here is the one previously we defined that explicitly here. Now we don't need that anymore. So we define that here inside this function, and that is something that is gonna be multiplied to the gradient. Okay, and when we say a stochastic gradient descent, it knows that our update is gonna follow this approach. Okay, so we have defined optimizer. Now we should be able to use that. Let's go inside our for loop, and inside the for loop here we have the loss function. We calculated the dot backbar. Now we can easily just use optimizer dot step. So this line is gonna do these two optimizations for us. Okay, so instead of these two lines, now I have this optimizer dot step. I also need to zero out the gradients. For doing that, we say optimizer dot zero grad. Instead of these two lines, we just use this line. Okay, now imagine that I have a lot of weights and a lot of biases. So instead of explicitly trying to type everything here, now we can have just one line that is going to do everything for us. So that's the way that PyTorch is going to save a lot of time for us. We also put this zeroing gradients after optimizing, but it's okay to put this also here before this. After you initialize the gradients, before taking derivatives, you can put it here. So it doesn't matter. Both of them are correct. So that could be here, or that could be here. Okay, now we should be able to run our model again and see the results. Let's do that. Let's initialize again and use this function and train for 10 epochs. Okay, so we saw that this is for after first epoch, and then we see the results after the 10 epochs, and we can plot the loss function, and we can see again we were able to train the model. Okay, we were able to train the model, and we also see that here our loss function, we explicitly define that inside our training loop. We usually don't do that. Let's have a separate function for that. We could have a function that gets two arguments, y hat and y, and it returns torch.mean, the difference between y hat and y to the power of 2. Okay, in this way I can just replace this line with criterion of y hat and y. Okay, and same thing here, just to save the loss value. Okay, let's now use this function. Let's initialize again the model and train it again. Okay, we are able to train that, and we can see the loss function. Okay, so in this way we are more organized. So whenever our loss function is more complex, so we can have more complex functions inside this method. Also, we have some predefined loss functions by PyTorch, for example, mean square error, and we can use them directly instead of define them explicitly. So for example, I can say criterion equals nn dot mean square error loss. Now we define our criterion here using PyTorch function, and we can comment out our previous criterion. And the way that we are going to use that inside the function is the exact same thing. It's going to get two inputs, so y hat and y. So everything will be similar. So let's run the whole code again, and we should be able to see, okay, the result is the exact same thing, and we are able to again to train the model. Okay, let's review our training process. In our training that we are using a stochastic gradient descent, we have a linear model that now we learned how to make a custom class like this one, and how to use the functions from the PyTorch. For example, here we use a linear function. And after doing that, we saw that we can initialize that. And after we have the model defined, we can just use the model here and get the prediction. And then we saw how to define our loss function using the PyTorch functions. For example, here we use the mean squared error functions from PyTorch. We can also have an explicit function that we define if we want to have our function be different than what is already defined in PyTorch. But many times we can just use the predefined functions. And then after calculating the loss function, we use the dot backward to get the derivatives with respect to w and b. And then for updating w and b, we use optimizer.step, and optimizer defined here as a stochastic gradient descent. And then we saw that we can zero out the gradients using this function. And this line actually can come here after doing the steps. We can zero out the gradients for the next step, or we can actually have this line before the calculating the gradients. So for example, here I can have the optimizer dot zero grad. So sometimes you see that is located here or after the step. Both of them are correct. So if it is here, it's all still correct, because before calculating gradients, we want to make sure that there is no gradients remaining from the previous steps. Okay, this is all we have for this session, and thank you so much again for watching this video.